Good morning, afternoon, or evening, everyone. My name is Nindhia with the student ID number ending in 080. Today, I will be presenting Chapter 5, Iron and Steel Production and Steels, from Manufacturing, Engineering and Technology by Srob Kapakjian and Steven Skimmitt. In this chapter, we will explore how iron and steel, the most important structural materials, are produced, refined, cast, and classified. We'll discuss the processes from raw materials to high-performance alloys, including carbon steels, alloy steels, stainless steels, and tool steels. Let's begin with an introduction to the importance of iron and steel in manufacturing. Iron and steel dominate modern manufacturing. They make up almost 90% of all metal usage. The combination of high strength, formability, and cost-effectiveness makes steel essential for producing ranging from building to cars and machinery. The production route typically begins with iron ore, which is reduced to pig iron in a blast furnace. Pig iron is then refined to remove excess carbon and impurities, forming steel, a material whose composition and microstructure can be precisely controlled for different applications. The production of iron and steel forms the foundation of the entire manufacturing industry. In this section, we'll take a closer look at the two essential stages, iron making and steel making, and understanding how raw materials are transformed into the most widely used engineered materials in the world. First, let's consider the significance of these processes. Steel accounts for about 90% of all metallic materials used globally. Its versatility and strength make it indispensable in construction, transportation, energy system, and consumer goods. The overall process starts with iron making, where the goal is to reduce iron oxide from the ore into molten iron, known as pig iron. This process typically takes place in a large vertical structure called the blast furnace, which operates continuously for years at a time. Once we have molten pig iron, we move to steel making, where the focus shifts from extraction to refinement. Pig iron, while rich in iron, contains excessive amounts of carbon, about 4%, along with impurities such as silicon, sulfur, phosphorus, and manganese. These impurities make pig iron brittle and unsuitable for most engineering applications. Therefore, the steelmaking stage involves controlled oxidation to remove unwanted elements and adjust the carbon content to below 2%, giving us steel with the right balance of strength, ductility, and toughness. To summarize, iron making extracts, while steel making refines. Together, they form a continuous and interconnected process, transforming raw materials from the earth into the building blocks of modern civilization. Now, before delving deeper into iron making, let's talk about the essential raw materials. Three primary materials are used in blast furnace: iron ore, coke, and limestone. Iron ore provides the iron content. The two most common ores are hemanite and magnetite. These ores are first crushed, screened, and sometimes pelletized to improve uniformity and furnace efficiency. Coke, derived from metallurgical coal, serves two vital functions. First, it acts as fuel, generating the extreme heat needed to melt iron. Second, it provides carbon monoxide, the reducing agent that removes oxygen from iron oxide. Without coke, the chemical reduction of iron will not occur efficiently. Next, we have limestone, which serves as fluxing agent. As the ore melts, impurities such as silica and alumina combine with the limestone to form a molten slag, which floats on top of the iron and can be easily removed. Finally, hot air, preheated up to about 1000 Celsius, is blown into the furnace from the bottom through tuyeres. This provides the oxygen necessary for the combustion of coke and the generation of reducing gases that drive the entire processes. Figure 5.1 shows an illustration of a blast furnace. Now, let's move on to iron making, which takes place in the blast furnace, as I showed before. Inside, temperatures ranges from around 200 Celsius at the top to nearly 2000 at the bottom. The operation is continuous. Fresh layer of iron ore, coke, and limestone are charged from the top, while molten iron and slag are tapped from the bottom. The key reaction begins as the hot air reacts with coke, forming carbon monoxide. This carbon monoxide then rises and reacts while the descending iron oxides. Through a series of steps, the iron oxides are reduced to metallic iron before reaching the hottest zone at the furnace base, where they stay melt and collect as liquid pig iron. The limestone flux decomposes into calcium oxide, which reacts with silica and other impurities to form slag. The slag floats on the top of the molten iron due to its lower density, allowing it to be separately easily. The products of the blast furnace are first molten pig iron, about 4% carbon tapped from the bottom. Second is the slag, a byproduct that can be used for cement or road construction, and 3 hot gases, mainly carbon dioxide, which are cleaned and recycled to preheat the incoming air. The result of the stage is pig iron, a crude form of iron that now serves as the feedstock for steel making. The chemistry and efficiency of this process determine both the cost and quality of steel production worldwide. Once the molten pig iron leaves the blast furnace, it enters the steel making stage, where the true transformation occurs. The goal here is to reduce the carbon content from roughly 4% to a controlled level, typically around 0.02 until 1.5%, and remove impurities like sulfur, phosphorus, and silicon. 2 primary methods are used today: the basic oxygen furnace, or the BOF, and the electric arc furnace, the EAF. In the basic oxygen furnace, molten pig iron is poured into a large refractory lined vessel. A high purity oxygen jet is then blown at a supersonic speed onto the molten surface. This oxygen reacts vigorously with carbon and other impurities, which form gases which escape from the melt. This process is fast, typically less than an hour, and is capable of producing large batches of steel efficiently. It now accounts for roughly 70% of the world's steel production. The electric arc furnace, in contrast, primarily melts scrap steel using electric arcs between graphite electrodes. It offers flexibility, lower capital costs, and is more environmentally sustainable due to its ability to recycle scrap metal. EAFs are especially favored for producing specialty and alloy steels. After refining, alloying elements may be added to achieve specific properties. The molten steel is then tapped and directed to the casting stage, either into molds or through continuous casting lines. Overall, the transition from pig iron to refined steel is not just a physical change, but a controlled chemical evolution, resulting in a material whose strength, ductility, and toughness can be precisely engineered. This figure 5.4, shows the 3 main furnace designs used in the steelmaking process, each serving a unique purpose depending on the scale, energy source, and purity requirements of the steel being produced. Starting with figure A, on the left, this is an electric arc furnace. It uses large carbon electrolytes to which electrical energy is supplied in the form of high-temperature arc. The arc melts the charged material, typically a mixture of scrap steel, direct reduced iron, or pig iron, producing molten metal at the bottom of the furnace. Inside the vessel, we can see that the round heart where the molten metal collects, and the slag layer that forms above it, capturing impurities. The EAF is highly efficient, flexible, and environmentally friendly since it can recycle steel scrap repeatedly. Next, in figure B, which is the middle one, this is a submerged arc furnace or direct arc furnace. In this configuration, the electrodes are positioned horizontally and can make direct contact with the molten metal. It's mounted on terminums and rollers, allowing the furnace to be tilted for pouring molten metal or slag. This design ensures intense and uniform heating, often used for ferroalloy and high-carbon steel production, where deep heat penetration is necessary. Finally, in figure C, on the very right, we have the induction furnace. Unlike the previous 2, it does not rely on electrical arcs or combustion. Instead, it uses electromagnetic induction generated by copper coils surrounding a refractory line cubicle. The alternating magnetic field induces electric currents within the metal charge, heating and melting it directly. Because it doesn't use electrodes or produce slag, the induction furnace is ideal for melting small batches of high-quality specialty steel and alloys where purity and control are crucial. This figure illustrates the sequence of operating in the basic oxygen furnace, one of the most important and widely used steelmaking process. In the first image, we see the charging of scrap steel into the furnace. Scrap serves two purposes. It acts as a coolant to absorb the intense heat generated during the oxidation reaction, and it also helps recycle steel waste, making the process more sustainable. Next, in the second image, molten pig iron from the blast furnace is poured into the vessel. This molten iron contains around 4% carbon along with impurities such as silicon, sulfur, and phosphorus. In the third image, we add burnt lime and sometimes dolomite. These fluxing materials help combine with the impurities to form a molten slag that floats on the surface and can later be removed easily. Now, in the fourth image, we see the heart of the process, blowing oxygen through a lance. A water-cooled oxygen lance is lowered from the top, and high-purity oxygen is blown at a supersonic speed directly onto the molten metal. This oxygen reacts vigorously with carbon, silicon, and other impurities, producing oxides, which either escapes as gas or becomes part of the slag. This reaction is highly exothermic, generating the heat needed to keep the steel molten without adding fuel. After refining, the next step, shown in the fifth image, is tapping the furnace. Tilting the vessel to pour the refined molten steel into a ladle of further processing or casting. Finally, the last image shows pouring of the slag, which is skimmed from the top and processed separately after use in construction materials. The entire BOF process typically takes less than an hour, yet it produces hundreds of tons of high-quality steel in each batch. Its efficiency, speed, and ability to produce clean, precisely controlled compositions make it the dominant steelmaking methods worldwide. The next step after steelmaking is casting, where molten steel is poured into molds to form ingots. As the metal cools, solidification begins from the mold walls inward, creating zones of varying composition due to segregation, gas evolution, and volume contraction, often form shrinkage cavities. After solidification, the ingots are stripped from molds and reheated for further shaping into bloom, billets, or slabs. Continuous casting revolutionized steel production by eliminating many drawbacks of ingot casting. Here, molten steel flows through a water-cooled copper mold, solidifies into a strand, and is continuously drawn downward while being cut to desired length. This process improves productivity, minimizes waste, and produces more homogeneous structure. It's now the dominant casting method worldwide, ensuring better surface finish and less segregation compared to traditional ingots. This figure shows the continuous casting process, which has almost completely replaced traditional ingot casting in modern steel production. It's a highly efficient process that converts molten steel directly into solid slabs, billets, or blooms, eliminating several intermediate steps. Now let's walk through how the system works. At the very top, we have an electric furnace, or sometimes a ladle, from a basic oxygen furnace, which delivers molten steel into a tundish. The tundish acts as a reservoir and distributor, controlling the flow of molten metal into the mold through a ceramic nozzle. It also helps maintain a steady pouring rate and temperature, ensuring smooth operation. Next, the molten steel enters a water-cooled copper mold, seen here in the vertical section. As the steel comes into contact with the cold mold walls, solidification begins at the outer surface, forming a thin shell while the interior remains molten. The partially solid strand is continuously withdrawn downward by a series of pinch rolls. To prevent oxidation, argon gas is often used to create an inert atmosphere above the molten pool. Meanwhile, cooling water circulates around the mold along the solidified strand to promote uniform heat extraction. Below the mold, the strand passes through secondary cooling zones where a spray of water continuously to solidify the remaining liquid core. By the time it reaches the pinch roller near the bottom, the steel is completely solid. On the right hand of the side of the figure, we see additional equipment such as backup rolls, suction pulleys, and synchronized pitch rollers, which ensures the strand moves smoothly without cracking or bending. The X-ray receiver monitors the metal level in the mold, allowing precise control of the pouring rate. Continuous casting offers several major advantages. It improves yield, reduces segregation and porosity, ensures a more uniform structure, and significantly reduces production costs and energy consumption compared to traditional ingot casting. Steels are generally classified as carbon or alloy steels, depending on their composition. Plain carbon steel contains primarily iron and carbon with small amounts of other elements. Adding alloying elements like nickel, chromium, molybdenum, and vanadium improves strength, toughness, and corrosion resistance. Through controlled heat treatment, these steels can achieve a wide variety of mechanical properties, making them ideal for structural and engineering uses. Each alloying element serves a specific purpose in modifying steel properties. Carbon primarily determines hardness and strength. Manganese acts as both a deodizer and a tough enhancer. Silicon strengthens the ferrite phase, while chromium, vanadium, and tungsten form carbides that resist wear at high temperature. Nickel, on the other hand, contributes to toughness and corrosion resistance. By carefully adjusting these elements, engineers can tailor steel for extreme performance environments. This table shows the applications for selected carbon and alloy steels. Residual elements are those unintentionally present in steel, often introduced from recycled scrap or impurities in ores. Elements such as copper, tin, arsenic, antimony, lead, and bismuth can accumulate and adversely affect properties. For example, lead and bismuth may cause hot shortness, making the steel brittle by high temperature. To control these effects, producers use secondary refining or dilution with virgin materials. Residual control ensures consistent performance in structural and high-quality applications. Steels are categorized by a standardized numbering system to indicate composition and applications. The AISI SAE designation is most common. It uses a 4-digit code where the first 2 digits identify the alloy type and the last 2 digits indicate carbon content in hundredths of a percent. For example, 1045 or 1045 means a plain carbon steel with 0.45% of carbon. Alloy steels such as 4140 or 4340 represent chromium, molybdenum, and nickel-chromium molybdenum steel respectively. These systems simplify communication between engineers, manufacturers, and suppliers globally. Carbon steels form the largest group within the steel family, and their mechanical properties depend primarily on carbon content. Low carbon steels are soft and easily shaped, making them ideal for automotive bodies and structural applications. Medium carbon steel balance strength and ductility, suitable for axles, gears, and machinery parts. High carbon steel offers high hardness and wear resistance, used for springs, blades, and high-stress components. Heat treatment further enhances their strength and service life. This table presents a comparison of the mechanical properties of various carbon and alloy steels, specifically illustrating how compositions and heat treatment influence their strength, ductility, and hardness. Now, let's look at the columns carefully. The table lists 4 representative steels by their AISI designation: 1020, 1080, 3140, 4340, and 8620, each tested under different conditions such as rolled, normalized, and annealed. Overall, this table clearly demonstrates how both composition and heat treatment determine a steel mechanical behavior. Low carbon steel provides ductility and weldability. High carbon steels provide hardness, and alloy steel balances strength, toughness, and heat-treated response. This allows engineers to select the optimal grades for each application. Alloy steels represent a major class of steel where small but deliberate additions of other elements are made to enhance specific mechanical and physical properties that plain carbon steels cannot achieve. Unlike plain carbon steel, which consists mainly of iron and carbon, alloy steel contains significant qualities of elements such as manganese, nickel, chromium and molybdenum, vanadium, tungsten, and sometimes copper or silicon. Each of these elements alter the microstructure, hardenability, and performance of the steel in distinct ways. The goal of alloying is to improve strength, toughness, hardenability, corrosion resistance, and wear resistance, depending on the intended application. One of the key advantages of alloy steels is their hardenability, the ability to form marzenite not only at the surface but throughout the entire cross-section during quenching. This makes it possible to produce thick or large components with uniform mechanical properties from surface to core. Alloy steels are also highly responsive to heat treatment. By controlling processes such as annealing, quenching, and tempering, engineers can tailor a microstructure ranging from ductile ferrite to extremely hard marzenite or bionic form. The versatility allows alloy steels to be used in a wide range of critical components, including gear, shafts, connecting rods, crankshaft, and aircraft parts, and many others. For example, steels such as AISI 4140 or chromium molybdenum steel, and the 4340, which is a nickel chromium molybdenum steel, are widely used because they offer an exceptional balance of strength, toughness, and fatigue resistance, even under heavy loads or cyclic stresses. However, alloying must be done carefully. Adding too many elements can increase costs and reduce reliability or machinability. Therefore, modern alloy steels are designed to achieve the maximum performance with minimal alloy content, optimizing both material efficiency and mechanical performance. In summary, alloy steel combines the best of both worlds: the strength and toughness of carbon steel enhanced by alloying elements that extend their performance limits. They form the foundation for many high-performance applications where durability, heat resistance, and reliability are critical, and safety and function. High-strength low-alloy steels, or HSLA steels, are designed to combine high strength with good ductility and weldability, all while keeping carbon content low, usually below 0.2%. Their strength comes from very small additions of elements like vanadium, niobium, and titanium, which are fine grain sizes and form hard precipitates that harden the steel, that strengthen the steel. HSLA steel offer yield strengths from 400 to 700 NPa and are lighter and tougher than traditional carbon steel. They are used for bridges, pipeline ships, and structural components, where both strength and weight reduction are vital. They also have good corrosion resistance, especially when copper is added. Figure 5.5 here is a comparison of advanced high-strength steels. And then here are the mechanical properties of high-strength steels. And then this is for the AISI designation, as I have explained before, but this is for high-strength sheet steel. Then moving on, we're going to go to ultra-high-strength steels, or UHSS. They take performance even further, reaching yield strength above 1000 MPa. These include quenched and tempered alloy steels, martensic steels, and marine steels. Their strength comes from martensic or precipitation-hardened microstructure, allowing them to handle extreme loads while remaining relatively light. They're used in aerospace, defense, and high-performance vehicles, where strength-to-weight ratio is critical. However, UHSS are less ductile and require careful heat treatment to prevent brittleness. Even so, they represent the cutting edge of steel technology, combining maximum strength, fatigue resistance, and efficiency. Now, this is an example of a high SSS, or a high-strength steel, which is used in the Ford 500, used in the applications of the Ford 500. Stainless steels are defined by at least 10.5% chromium, which forms a thin protective oxide film that prevents rust and corrosion. They're divided into three main groups. First is authentic stainless steel. They are non-magnetic, highly corrosion resistant. They're used in food, chemical, and medical equipment. Next, we have ferrite stainless steel. They are magnetic and economical, used in automotive and appliances. Next, there is martensic stainless steel. They are hardenable by heat treatment, used for cutlery and surgical tools. Each type offers a balance of corrosion resistance, strength, and formability, making steels vital for industries that demand both durability and aesthetics. Table 5.6 shows the basic types of tools and die steels. And then this table just shows the processings of the high strength steels and the characteristics of common tools and die steels. Now there's also high speed steel, HSS. They are special tool steels for cutting tools that operate at high temperature. Their defining feature is red hardness, the ability to stay hard up to 600 Celsius during high-speed machining. They contain tungsten, molybdenum, chromium, vanadium, and cobalt, forming strong carbides that retain sharp edges. The T series, or the tungsten base, and M series, the molybdenum base, are the two main types. HSS is used for drills, mining cutters, taps, and lethal tools, enabling precision machining in nearly every manufacturing industry. Die steels are used for forging, stamping, extrusion, and die casting, processes that require both heat resistance and toughness. They are classified into hot work steel, the H series, used at high temperature, resist softening and trouble fatigue. There is also cold working steels, or the D series, used at room temperature for forming and punching. Proper heat treatment gives them the ideal balance between hardness and toughness. Die steels are essential because they maintain shape and precision while forming thousands of metal parts, ensuring consistency, quality in large-scale manufacturing. This table summarizes the types of tools and die materials typically used for different metalworking processes, and it highlights how the choice of material depends on the working condition, such as temperature, pressure, and wear environment. So let's go through the main idea. For die casting, materials like H2 and P20 steels are used because they can withstand high temperature and thermal cycling, as molten metal is repeatedly injected into the mold. These are known as hot work tool steels. They are valued for their ability to resist softening and cracking under thermal fatigue. In powder metallurgy, punches and dies are often made from D2, S7, or M2 steels. They require high hardness, compressive strength, and wear resistance during compaction of powders. For mold for plastics and rubbers, materials such as S7, P20, H13, and 6F6 are common. They provide good polishability and corrosion resistance, ensuring smooth mold surfaces and long service life. When we move to hot forging, we see again the use of H-series steels like H11, H12, H13, which maintain their strength and toughness even at elevated temperature. In cold extrusion or cold heading, where deformation occurs at room temperature, steels like D2, M2, and WC, tungsten carbide, are selected because of their extreme hardness and resistance to wear. So those are just some of the examples of the typical tool and die materials for metalworking processes. To summarize Chapter 5, we've explored the entire journey of steel, from its production to its specialized forms and applications. We began by understanding how iron and steels are produced from raw materials such as iron ore, coke, and limestone, through iron making in the blast furnace and steel making in the basic oxygen or electric furnace. When we looked at how molten steel is cast into solid forms, either by ingot casting or the modern and efficient continuous casting process, which produces slab, looms, and billets ready for further shaping. After that, we examined the different types of steel, from plain carbon steels and alloy steels to more advanced categories like high-strength low-alloy (HSLA) steels, ultra-high-strength steels, and stainless steel. Each of these has unique composition and heat treatment response to give them the distinct combination of strength, toughness, and corrosion resistance. Finally, we discussed tool and die steels, including high-speed steels and die steels, which are essential for manufacturing other metallic products. These steels must maintain hardness, wear resistance, and dimensional accuracy even under high temperature and repeated stress. In essence, Chapter 5 shows how controlled chemistry, precise heat treatment, and intelligent alloy design allow engineers to tailor steels for virtually any purpose, from building bridges and automobiles to precision cutting tools and medical instruments. Steel remains the backbone of modern industry, and understanding its production and classified is fundamental to all fields of mechanical and manufacturing engineering. That is all that I have to offer for you guys today. Thank you so much for your attention, and I deeply apologize for any mistakes or oversights in this presentation. Thank you.